we're going to find the Taylor series for sine of x centered at a equals 0. Since I said centered at a equals 0 right here, I could have also said Maclaurin series, because centered at 0 is basically the definition of the Maclaurin series. So just to remind you there what the meaning of these different names is. We're also going to want to find its radius of convergence, and let's go ahead and do that. So I guess I'll write it down again. So the f of x has the Taylor series centered at 0 of sum from n equals 0 to infinity the nth derivative evaluated at 0 divided by n factorial times x to the n. Okay, and we're going to build our table again. So there's that. We'll also need an nth derivative, and we'll need an nth derivative evaluated at the center, right? If we can find a formula for this guy, then we just divide that formula by n factorial and we're done. Okay, so here's 0th derivative is sine of x, and plugging in 0 gives me sine of 0, which is 0. First derivative is cosine of x, and plugging in 0 gives me cosine of 0, which is 1. And another derivative, now we have minus sine of x, minus sine of 0, 0. For n equals 3, we take another derivative, so now we have minus cosine of x. And plugging in 0 minus cosine of 0 gives us a minus 1. N equals 4. Take another derivative. Derivative of cosine is minus sine, so we have a minus minus sign, or in other words, we're back to a positive sine of x. And plugging in sine of 0 again, 0. Let's do another one, and hopefully you'll catch on to the pattern right here. Doing another one, we got cosine of 0, and we're at 1 right here. Notice I don't have to go out any further in this calculation here, because this line is already exactly the same as this line, and the next line is already exactly the same as that line, right? So it's going to keep progressing in the, the exact same sort of, I don't know, color-coded pattern there. I don't really need to work out the next one. It's going to be 0, okay? So using that, this is going to be a much more difficult pattern to come up with a formula for, right? I mean, it's got to hit zeros, and it's got to, it's got to alternate zeros, and then in between the zeros, it's got to alternate ones and minus ones, right? So this is a little bit more of a difficult pattern to just write down a formula for just off the bat. I would say the best way to do this is to actually start by just writing down the Taylor series, not in sigma notation. Don't go for sigma notation. Do it more like how we were practicing with writing the sigma notation after you took a derivative, or finding the sigma notation after you took an integral, okay? So the Taylor series is centered at 0 is going to be, I'll call it t of x. It'll be the very first term, which is a 0. Then we're going to have our next term, which will be a 1 divided by 1 factorial with a power of x to the 1. Next, we're going to have a 0. Right? And then we're going to have a minus 1. Right now we're right here, right? That's our minus 1. And that'll be an x cubed. And how about we just stop writing the 0 terms? Because, I mean, the next term is going to be 0 over 4 factorial x to the 4th. But our formula doesn't really have to capture the zero terms. It can just ignore them because they're zero. So let's, instead of doing that and writing things out this way, let's condense this down a bit and go for this formula. So I'm going to have 1 over 1 factorial x. I'm going to jump that guy, and now I'm going to have minus 1 over 3 factorial x cubed. And now I'm going to jump that guy, right? What's going to be next? Well, now we're on the 5th power term, right? The powers are going up by 2 because they're always skipping a 0 term. And the sign is alternating. So we're going to have now plus 1 over 5 factorial x to the 5th. And now, hopefully, you start to see what the pattern is. These odd numbers are alternating in sign. And you've always got the same odd power as you have in the factorial. So I'll do a bunch here. And there's no definite method to getting this done all the time. It's basically up to you to be able to spot the pattern and write a formula for whatever's happening here, So hopefully what I've got on the screen now is enough for you to spot the pattern and write a formula for it. Okay. Writing a formula always begins with picking n values. So let's say this is n equals 1, n equals 2, n equals 3, n equals 4. How can I predict what comes next, right? That's what we're basically asking right here. And think about it a little bit. The odd numbers are always going to be twice the n that I'm on minus 1. And so that's my predictive formula there for at least what's down in the denominator and what's up in the numerator. And then we're just going to need to include a sign there, right? So our Taylor series will be the sum from n equals 1 to infinity. An alternating sign that begins positive, and in the denominator we have a 2n minus 1 factorial, and in the numerator we have a 2n minus 1. And this is the Taylor series centered at 0 for the sign of x. I should point out that this is not the Taylor series that you will see in the book, because I used a different convention when writing this thing out. And there will always be a different convention. There's never one right way to do it. So for instance, I could solve this problem entirely differently by proceeding this way. What if instead I wanted to come back here and call this n equals 0, and then call this guy n equals 1, and then this guy n equals 2, and this guy n equals 3? What's the formula for that going to look like? Well, you're still going to need an alternating sign up and top, and you're still going to need, whatever goes in here to be whatever goes in front of the factorial here to be the same, right? But if this is 0 and I want to get out 1, and this is 1 and I want to get out 3, and this is 2 and I want to get out 5, then what I'm doing now is I'm multiplying n by 2 and adding 1 instead of multiplying n by 2 and subtracting 1. So you will also see this formula. I think this is actually the one that appears in the book. Make sure it starts off on a positive sign. So now I'd want a minus 1 to the nth power, and 2n plus 1 factorial x to the 2n plus 1. All right, so remember, we haven't proved that sign is actually equal to this formula that I've found right here. That's for more to come. Factorials, you'll notice, are going to come up all over the place starting now. You want to make sure your factorial arithmetic and algebra is sound.